Hello everyone. In this video I am going to perform a piezoelectric energy harvesting, in this time on COMSOL. So when you open COMSOL you will see this screen first. We have two options to open a model. So you can directly open a blank model or you can use this one to have some instructions. So I will continue with this one. The first one, it asks for the space dimension. So we can also make the analysis in 2D, however, I will continue with 3D. And it asks for the physics. So if you search for the piezo, you will make piezoelectric analysis. So if you select this one, it will automatically add physics you need to make a piezoelectric energy harvesting. So electrostatic, solid mechanic, and piezoelectric effect. Apart from them, I want to add a circuit physics. So we will add an electrical circuit between the piezoelectric material. So I need to add this one also. And if you click study, it was to select one of the studies. So I will make the study in frequency domain. So I am selecting this one. Double click. And this screen will show up on your console. So first thing to do is adding the geometry. To add geometry, you can use leveling options like to SolidWorks or AutoCAD, or you can import step files from other softwares. However, I will directly draw the geometry in COMSOL. So to mention, I will make the study of Alper Erturk from the book of Piezoelectric Energy Harvesting. So the geometric and material properties of the piezoceramics and substructures are given here. So I will repeat this analysis in COMSOL. This is a bimorph beam, so the piezoceramic is bounded on both sides of the substructure. So these are the length, width, and the thickness of the substructure. So let's draw this one first. So let's add a block first. So let's check it. The length is 24.53. However, it is in millimeter. To make it millimeter, you need to use this one, or you need to give the dimension in meter. I am using this one. So 6.4 millimeter, and the thickness 0.14. And this is the base position of base coordinate position. It is at the 0, 0, 0. So if you click build selected, it will make a block with these dimensions. And also I will make blocks for the piezoceramics. So the length and width is same, however the thickness is different. So I will copy these options. So it is written as width, depth, height. However, the width means the x direction. So it is our length. Depth is y direction. So it is our width. And the height is our thickness. So the thickness is 0.5. millimeter. If you pull directly this one, it will start from the base corner 0, 0, 0. However, we need to change the base of the height of the base as the thickness of the block 1. So it will start from the end of the block 1. So it starts from here now and goes with an height of this one. And the other block, let's duplicate this. So these dimensions are directly from here. And this one I will use as base corner, however in minus. So it will start from minus this one and go through the 0 corner. So we have the substructure and two piezoceramics here. And then we need to add materials. So for substructure, it uses the brass, and for piezoceramic, it uses the PZT5H. So for materials, we can add from library or we can add blank material. I will add from library. Let's open this one. Let's search for PZT5H. Most of the piezoelectric materials is given here directly. So this is PZT5H. They are all same. And add material from library again, and there is no brass here. However, I will use any other solid material and I will change the density and elastic measures for the brass. So I am looking for aluminum and not this one. It's a built-in material and I will select this one. Let's close this. For aluminum, the density is 2700. However, I will change it to the 9000. And the Young modulus is 105. The Poisson ratio is not given, so I will leave it like this. And the other properties are not important for our study, so I will leave them as like this. So let's change the name of the material as brass. So the first material is applied on all of the domains. However, domain 2 is not piezo, it is a brass. So I deselect this one. So only 1 and 3 is piezo and the brass is this one. So you can directly select from here. So we added the materials. Now let's continue with the electrostatics. These are charge conservation, zero charge, initial values are directly coming with this option. I am leaving this as like this. However, we need to add ground and terminals to connect piezoelectric materials to each other. You can connect them by parallel. To make them parallel, you can select this one and this one as ground and the other two faces as terminal one. However, in this study, it uses the serial connection of the piezoelectric materials. So to make a serial connection, you need to select one ground. You need to give terminals to these faces. So let's go to the component and select domain option from here. And if you click this one, you can hide this domain and go to terminal 1 again. And this face and this face, I want them to be the terminal, and they are connected with a circuit. And terminal 2 is this one, and it is again circuit. So this is ground, and this is the face where I will measure the voltage. And these two faces are used to connect two piezoelectric materials each other. However, let's go to the component option and let's click this one to show up the this material again, this domain again. The piezoelectric materials is directly polarized in plus Z direction. So these two materials are polarized in same direction. However, to make a serial connection, this one should be plus Z and this one should be minus Z, or the vice versa. This one should be minus Z, this one should be plus Z. You can change material properties to make it, or you can change the directly the boundary system of one of the piezoelectric materials. So for this one, all of them in the same boundary system, so X, Y, and Z. Let's add another boundary system here, so coordinate system, not boundary. And let's add a rotated system. So rotated system means it rotates the boundary system as the degree what you give. Okay, so to make the one of them to change the direction of the polarization with 180 degrees in Z direction, we need to give a beta angle. So you can see here, so it rotates the Z. So if you rotate it with pi radian, it means 180 degrees. It means this rotated system has a minus Z according to the boundary system. So if you go to solid mechanics, we will use this rotated system later. If you go to the solid mechanics after the electrostatics, these are coming directly with our studies, and there is piezoelectric material. So this is piezoelectric material, this is not piezoelectric material. We need to deselect it. And I will deselect this one also because they are not polarized in same direction. So when you click piezoelectric material, these are options you can change. So you can use stress charge form, strain charge form. It is up to you. And also you can use elasticity matrix from material, or you can directly give it by yourself. Also relative permittivity, permittivity and mix formulations. And let's add another piezoelectric material, or let's duplicate this one. So now let's deselect this one. This is the piezoelectric material one. This uses the global coordinate system, and for this one I select this and I will use rotated system. So when you change the coordinate system of this one, it means one is polarized in plus z direction. However, this one is polarized in minus z direction because the minus z is plus z for rotated system. Okay. After we define the piezoelectric materials, we can define an electric circuit. So there is something here. So for electrostatic, we need to deselect this one. So this is electrostatic, but brass is not electrostatic material. So these three of them is solid mechanics, as solid mechanics option, and for electrical circuit. So we need to define a electrical circuit between piezoelectric materials to measure the voltage. So we need a ground node, okay. We will use a resistor and also we need an external terminal. Okay, so this is ground. Ground is not zero, and the terminal is terminal 2, not 1. 1 is used to connect each other only. So there is a circuit now between ground, this phase, and the external 2, terminal 2. And between these nodes, we can actually we need to apply a resistance to measure the voltage. So if you give very low resistances, it like 1 to something, it means it will act as short circuit. Or if you give very large, like 1 million or something, it will be close to the open circuit condition. So for Alper Erturk study, it used this one, like it is around 1 million ohm. So I will use this one. So this is 1 million ohm. It's near the open circuit condition. Okay, and the piezoelectric effect, this one has. Okay, and mesh, you can make different meshes. However, I will use the element size as normal, and I will use physics control mesh. This is not a complex study, so I use default option. However, you can change them by yourself if you want, or you can add directly from here to 330 swap, and size, distribution, etc. And last step is the frequency domain options. So we will make the analysis from 0 to 1000 Hz. So frequency should be between, if you click this one, you can add start is 0 or let's start with 1. Step is you can give 1, however I will use 10 to make it fast, and the stop will be 1000. Okay, so the frequency from 0 to 1000. Last thing, I forgot. We need to apply force or displacement or something. So in solid mechanics, if you right click, you can apply boundary loads, fixed constraints, etc. So this is base extension model. This analysis is made with the base extension. So I will apply a prescribed acceleration from one of the sides, and I will give acceleration in x direction 0, y direction 0, and in z direction let's give 1g acceleration. Okay, so we will apply an acceleration in z direction from here, and the other face is free, and with this acceleration we will measure the voltage from here. Okay, then go back to the frequency domain and click compute. There are some errors. Turn on into, sorry, this should be 2 and 1. Between 0 and 1, I think. Let's compute again. Why? Yeah, okay. It start to solve. Uh, so ground node should be 0 because ground is 0, and the terminal should be 1, 0 and 1, and the nodes should be, the resistor should be between 0 and 1. It directly gives 3 to something, so it gives errors. Okay, after some time it gives the results. So this is the results section. The electric potential, electric field, and stress is given in default. However, I want to see the voltage response in frequency domain. So I will add a 1D plot and I will add a global variable here. So you can directly write the expression or you can find the results from here. So from electrical circuit, you can select the node voltages. So for node 0, it is the 0 voltage. However, we can check the voltage in the node 1. If you click this one, it will give the voltage option, voltage result. So if you click plot, it will draw voltage in frequency domain. However, if you need to take the absolute values, okay, plot again. So this is the voltage response. Let's check the result of the Alper Erturk. So it is similar. Actually, the peak is around 500 and the peak. Actually, I forgot to add the damping. So our result is a bit higher than this one. But if we add damping, it will be closer to this result. So this is okay, and this section is because of the experimental setup. So in model, actually there is nothing like this. It will look better. So in model it comes straight. However, in experimental it gives this peak. It is because of the experimental setup. So the result is very close. To add damping, you need to go to the solid mechanics and select uh, where is damping. Sorry. Uh, Sorry, we need to add it from here, from the material. So go to the material. To add damping, you need to go to the solid mechanics and click the material, for example, for linear elastic material, and right click and add damping. So you can select Rayleigh damping, you can give the alpha and beta, or you can give the damping ratios in different frequencies, or you can add isotropic loss factor, anisotropic loss factor, viscous damping, maximum loss factor, etc. So there are options. Also, you need to add damping to the piezoelectric materials. You can add or don't add. So it's like this. Thank you for listening. If you have any question, please write below the video. Thank you.